Welcome back to another hansonmath.com video, and thank you for watching my YouTube channel. Today's video will deal with the usage of TI-84 graphing calculator for the calculator active portion of the AP Calculus AB exam. If you're one of my students at Pioneer High School, you will have a blank copy of this in your Schoology folder. And if you are not a student of mine, you can access a blank PDF copy in the description for this video. So without further ado, here we go. The first thing I would suggest is, especially if you're also a physics student, is to make sure your calculator is in radian mode. Any question on the test that requires trig functions requires you to be in radians. So I'm going to hit mode and make sure we're in radians. So let's see. Yep, we're in radians. So that's perfect. So now I'm going to hit second mode, which is quit, to get to the home screen. And we're going to look at question A from our sheet here. It says, what is the velocity of the particle when t equals 2? Well, we're given a velocity function. The velocity function is negative 0.1 times e to the x times cosine of x squared plus x minus 2. And the domain, the usable domain, is t equals 0 to t equals 3. So since we were given a velocity function and they ask us what is the velocity at time t equals 2, I'm going to go into y equals, and I'm going to enter in that function, which I already did ahead of time. Okay, so if you need to pause the video to catch up, go ahead to work along with me. That is the velocity function. So at this point, there's several things we could do. One thing we could do is we could go back to the home screen by hitting second mode, which is quit, second mode. We could recall that function instead of entering it in again, which is unnecessary to recall it. There's several ways. The way that I'm the most comfortable with is hitting variables, which is vars, arrowing over to y variables, y vars. It is a function, enter, and I do want y1, enter. So that's the velocity function, and to evaluate it at time equals 2, I put in parentheses 2 and evaluate it, and there it is. The velocity is 0.4829, and we do not have units here. This problem was not that specific. It could be meters per second or inches per minute or anything. So that is the velocity. The other way to do that is to look at the graph, and if you, depending on how you have your window set, it might look like that, some kind of crazy oscillating function. All right, but the prompt says that the interval is t equals 0 to 3. So I'm going to go over to window, and I'm going to make my x min and x max, which is time, set to the usable domain, which is 0 to 3. Now I'm going to hit graph and take a look. Okay. That's what I need to see, but we have all this unusable space because the graph appears to go no higher than 2 on the y-axis and no lower than negative 2. So I'm going to hit window once again, and I'm going to set my x min to negative 2 and my x max to positive 2, and then take another look at the graph. And to me, that's much better. Okay. This is the velocity graph again that we're looking at. So if I want to know what is the velocity at time 2, I can hit trace 2, enter. And again, we get 0.4829, and that is the velocity. So two ways to do it. You can do it from the home screen, or you can do it right on the graph by hitting trace. So that is the solution to question A. Question B is, how many times is the particle at rest over this interval? Well, the particle would be at rest when the velocity is 0, which means it has no velocity. So it's at rest when the velocity is 0. So where is the velocity 0? The velocity is clearly at 0 at the following places where it crosses the x-axis. You'd have a velocity of 0 here, 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 and we'd have to zoom in. But if I hit trace and we trace along this curve, we can see that here I have negative y values, and then it switches to positive y values. So it crosses the x-axis somewhere in here. Okay, so to answer part B, how many times is the particle at rest? Well, when the velocity is 0, we have 4 instances of that. Okay, so B, we have 4 instances. C, at what times is the particle at rest? So we need to find the x value of here, 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 and here. So to use that on the TI-84, that would be the 0 function. So if we go into the calculate menu, which is second trace, calculate menu, second trace, this would be function 2 for 0. So if I hit 2, okay, I want to approach this intersection, but the left bound means I have to be to the left of the intersection between the blue curve and the x-axis. So the left bound, that looks fine, enter. The right bound, I have to hit the right cursor to I'm clearly to the right of that x-intercept. Hit enter. Gas really doesn't matter too much. You can try to put the cursor right on where you think it should be. Enter. And then lo and behold, there is your 0 or x-intercept at a time of 0.324. Okay, so that's 0.324. You'd repeat the process. You do the same process. You do it again. Second trace. Number 2 is your 0 finder to find this one. Here I am. I'm to the left of the velocity being 0. Enter. Now I need to be to the right of the velocity being 0. Now I put it right on there. And there's my second time. Okay, this is a rounding error here. This really is approximating y equals 0. This is scientific notation. So it happens again at 1.4546. And then we have it down here. To save time, you can do it again. This should be 2.138 or thereabouts. And this next one would be 2.678. The AP test stipulates accuracy to the third decimal place or the thousandths place. However, one could make a case that it's safer to go more decimals, such as 4 to the 10,000ths for safety. Okay, but this is how you do this. Okay, that was question C. Question D is, what is the acceleration of the particle at each of the times it is at rest? So the acceleration would be the derivative of velocity. To get acceleration, you need the derivative of velocity. So to do that, I'm going to go to the home screen by hitting second mode, which is quit. The derivative on a TI-84 is math 8. So I'm doing math 8. The derivative is d over dx. So I'm going to use an x. And instead of typing in the function of velocity, the negative 0.1 e to the x times cosine, I'm going to recall that as y1 because it's still stored. So I'm going to go variables, y1. And we need to evaluate it at the 4 times when the particle was at rest. The first of which was, again, I should be using more decimal places. I believe I truncated it as 0.324. Okay, and that would be your acceleration because the derivative of velocity is acceleration. So we have some negative acceleration here, negative 0.227. If you want to do it again, an easy way to copy this function is by hitting second enter. Second enter will copy what you had. Now I'm just going to bump it back to my second time at which the velocity was 0, which was approximately 1.454. And the velocity, or excuse me, the acceleration this time is 1.6715. And you do this again for the next time velocity was 0, which was 2.138. And then again, you'd evaluate this same calculation, but when x is equal to 2.678, and there you will have your 4 acceleration values when the velocity was 0. Okay, that is how you do part D. Part E asks, over which intervals is the particle moving to the right? Well, the particle is moving to the right when the velocity is positive. So if we look at the velocity graph, again, and I bring out my highlighter here, or I'll just switch to orange. How about that? I'll use my orange highlighter. Here we go. The particle is moving to the right when the velocity is greater than 0. So the velocity is greater than 0 right in here. Okay, now it dips into the negatives. The velocity is greater to 0 here. And then again, it dips into the negatives. So now it's moving to the left, negative velocity. And it's moving to the right again when the velocity is positive once again, which is here to the end of the interval. So how do we write this? Well, we have our times here. The beginning of the interval was 0. So our velocity is positive. So the particle is moving right when the velocity function is greater than 0. So that would be from here to here, which is from 0 to 0.324, which we found earlier. We found those times in part C. Now the particle is moving to the left when it's below the x-axis, looking at the velocity function. From here, which would be 1.454. So 1.454 to here, which is 2.138 approximately. Okay, it's moving to the right because it's above, the velocity is positive. Now the particle is moving to the left because it's below the x-axis, negative velocity. And then from here, which is approximately 2.678, comma, to the end of the usable domain, which is 3. The velocity is positive. So those are the 3 intervals in which the particle is moving to the right when the velocity is greater than 0. Those are your solutions to part E. Okay, moving on to part F. What is the acceleration of the particle when t equals 2? Well, since we were given the velocity function, to evaluate the acceleration, we need to take the derivative of the velocity. So to do that, I'm going to go back to the home screen, which is second mode, which is quit. And we're going to take the derivative of the velocity to look at acceleration. So that would be math 8. Derivative is d over dx. We are plugging in the velocity function, which is stored as y1. So vars, y vars, enter. And we are evaluating it at time of 2. So t equals 2 or x equals 2. And lo and behold, the acceleration at time 2 is negative 2.313. Okay, so remember the derivative of velocity gives you acceleration info. Okay, question G is a good one. When does the particle have an acceleration of 1? So we'd have to set the v prime function equal to 0, or equal to 1, which is what we'd be really looking at, right? So velocity is v of t. The derivative of velocity can be thought of as a of t, acceleration, and you'd have to set that equal to 1 and solve if you're looking for when does the particle have an acceleration of 1. But since this is calculator active and time is of the essence, the smart money is to do the following. Let's take a look here at back to our graph. So I'm going to clear this and go to y equals. I'm going to leave this function here. This is the velocity function. I'm not going to delete it because who knows, I might need it again. I'm going to put the cursor on the equal sign and hit enter to disengage this function. It doesn't clear it, it just hides it. So now if we hit graph, you see nothing. So I merely hid the graph. I might need it later, so I'm not deleting. Arrowing down to Y2, I want to be able to look at the acceleration picture, which is the derivative of this velocity function. So to look at the derivative of velocity, I'm going to do math 8 d over dx of the y1. So again, that's vars, y vars, enter, enter. And the trick to see the graph of acceleration is to do x equals x. X equals x will let us look at the acceleration function. And I'm going to do one more. I'm going to set the graph of y3 equal to 1, which is our target acceleration. Now I'm hitting graph. This red curve is literally the plot of acceleration, and the black line is showing an acceleration of 1. So when do we hit an acceleration of 1? We hit it here, 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 and here. So there's literally 4 times at which the acceleration is exactly positive 1. So how do you find this one? Well, we're looking for this time or this x coordinate down here. How do we find that? Well, again, time is of the essence. We should use the intersect function. Okay, I'm only going to do one. I'm not going to find all 4 due to time. You can do that. So how do we do intersect? Well, it's in the calculate menu, which is second trace, and we want intersect, which is on TI-84 option 5. Option 5, it says first curve. Well, I like to put the blinker on where the intersection looks by eye, and I hit enter. Second curve, it switched from the black line to the red curve, but we're still right there. So second curve, enter, and guess we're good, enter. And there it is. We have an acceleration of 1 when the time is 1.3184. Okay. And you do the exact same thing to get the other ones. Again, you'd have to do second trace, intersect. Now I'm going to move the cursor over to the next intersection right here. And I'm simply going to bump through enter 3 times. First curve, enter, second curve, enter, guess, enter. And without further ado, you have another timestamp when the acceleration is 1. That time is 1.7895, etc. Rinse and repeat for the next 2. The intersection feature is tremendous when you're looking for when something happens. All right, that will bring us to part H and I, which are related. H and I, H says, when does the particle reach its maximum velocity? And I says, what is the maximum velocity? Now, there are several ways to do this, but for me, I'm thinking if I can look at the picture of velocity, the maximum is literally your biggest Y value. So again, I'm going to hit clear, get my bearings here, and I'm going to go to Y equals. Now I'm thinking to myself, if I want to look at maximum velocity, I want to look at the velocity function, which I stored in Y1. So I want to put the cursor on the equal sign and reactivate Y1. And I'm going to deactivate Y2 by hitting enter on the equal sign. And I'm going to deactivate Y3 by hitting enter on the equal sign. Even though I know I'm not going to have to use them because this is the end, maybe you want to use it in the future. So now all I have activated is the velocity function stored as Y1. So I hit graph. There we are. Part H, when does the particle reach maximum velocity? Well, the maximum velocity is it could be an endpoint, but it's not, because the highest position of this velocity function, remember, we're literally looking at V of t, is right here. So I need to find the x coordinate right there to find the when the velocity is at its absolute maximum. So to do that, we need the maximum finder. The maximum finder, again, is in the calculate menu. That would be second trace, maximum, which is option 4 for me. The left bound means I need to trace over and be slightly to the left of the top of the hill here, like that. Enter. Right bound is arrow over to the right of the top of the hill. Enter. Guess you could hit enter, or you can put it kind of on target, enter. And there it is. So the win is the time, which is your X value. So the win, which is question H, the win is this, right? So you'd write the particle reaches its maximum velocity when T equals 2.9379, let's say. Okay, that's your win. Now, if this had units, you'd have to put your units like minutes or seconds. All right, so make sure you write a sentence. The particle reaches its maximum velocity when T equals 2.9379 seconds, or whatever the units are. That's the win. Now, question I is the what. What is the maximum velocity? Well, that's your Y value. So the maximum velocity is 1.8679 feet when T equals 2.9379. So the what is the Y and the when is the X. All right, that is your crash course in the calculator functions, the basic ones for the AP Calculus exam. I hope this helps. Good luck. Good luck. Yeah. Good luck on your exams, everybody, and take care of yourself, and best of luck in all your future mathematical endeavors. Mr. Hansen is signing out.